One telescope keeps rewriting the rulebook. And this time, the clues don't come from one headline image. They come from a pattern. In this video, we'll connect Webb's sharp new looks at familiar targets, its chemical fingerprints of worlds in the making, and its most daring peaks toward cosmic dawn. You'll see how scientists turn faint infrared light into measurements, why some results feel ahead of schedule, and what must happen next to confirm the boldest claims. Stay to the end, because the pattern finally snaps into focus for this discovery. Start close to home, because Webb's new finding begins with a simple trick. It changes what counts as visible. When NASA released Webb's view of Neptune, the attention went straight to the rings, because they appeared with a clarity not achieved in decades. But the bigger point is how that image is made. Webb's near-infrared camera, NIRCam, captured Neptune in infrared, and in that kind of light, the planet's atmosphere and the ring system pop with totally different contrast than in visible images. That matters, because you can now treat faint ring structure as something you can track over time, not just admire once. In other words, it becomes a monitoring tool, not a postcard. Now pivot to a famous target that almost everyone thinks they already know. Pillars of creation. Webb's near-infrared view isn't a remake, it's closer to a depth scan. In this wavelength range, dust that blocks visible light can become partly transparent, which changes the story from giant shapes to what's hiding inside the shapes. NASA's own description stresses this is a living star-forming environment, so seeing deeper into it helps researchers separate glowing edges of gas from the embedded stars that are sculpting those edges. That shift is important because star formation models depend on correctly counting young stars and understanding how gas and dust are distributed, not just on how dramatic the silhouette looks. Then comes the moment that quietly upgrades this from pretty images into physics. In late 2025, NASA highlighted a truly immense protostellar jet in SH2-284 and made a specific scientific point. The observation supports the idea that jets scale with the mass of the parent star. More massive protostars can drive larger jets, hinting at a more universal star formation mechanism across different mass ranges. That's not just an exciting claim, it's a testable one. If the scaling holds across more objects, it tightens the rules of how stars build themselves, from small to massive. Webb keeps revealing hidden layers in systems we thought were already familiar. And once you accept that it's excellent at exposing what used to be invisible, the next question becomes irresistible. What happens when it points that same toolkit at planets, moon factories, and even visitors from other star systems? Here's where Webb shifts from "show me what's there" to "prove what it is." The Alpha Centauri story is a perfect example because it's both thrilling and brutally difficult. The Alpha Centauri system is close, but closeness doesn't make it easy. Bright stars create glare that can bury faint planetary signals. In 2025, NASA/JPL reported strong evidence consistent with a giant planet candidate around Alpha Centauri A using Webb data. The key idea isn't just a planet might be there. The key idea is that Webb is pushing direct detection methods near a bright star into territory that used to be out of reach. Now, instead of asking, "Is there a planet?" Webb goes one step more cinematic. Could there be a place where moons get built? In September 2025, NASA described spectroscopy of a disk around the young giant planet CTChaB and listed a set of molecules detected in that disk, chemicals consistent with raw ingredients for moon formation. That's a different style of result than an image. Spectroscopy is basically light forensics. You split the light into components and look for chemical fingerprints. When you can do that for material around a planet, you're not only observing an object, You're sampling an environment remotely. This is why the CTChaB result matters. It turns moons might form around giant planets from a theory you tell students into a process you can start to quantify with real measurements. Then comes the wildest sample in your lineup, an interstellar comet. ESA described how quickly observers mobilized after the discovery of Comet 3 I Atlas on July 1, 2025, and ESA's multimedia release notes that Webb observed the comet on August 6, 2025, using its near-infrared spectrograph, with teams analyzing the data to learn about its size, physical properties, and composition. That's the Webb era in one move. Catch something rare, then convert faint infrared signals into a chemical and physical profile. And because this object formed around another star, it's a direct comparison point for what building blocks look like outside our solar system. Webb keeps upgrading astronomy from guessing to testing. If it can challenge glare in the nearest stellar neighborhood, read the chemistry of a moon-forming disk, and analyze a true interstellar visitor, then aiming those same tools at the early universe isn't just logical, it's inevitable. To make the early universe results feel real, you need a bridge between nearby detail and ancient faint dots. That bridge is comparison and amplification. First, Webb mapped structure in 19 nearby, face-on spiral galaxies as part of PHANGS. The point isn't that spiral galaxies are shocking, it's that Webb delivers consistent near- and mid-infrared views that let researchers compare stars, gas, and dust on fine scales, while tying those insights to other observatories across different wavelengths. That matters because understanding how star formation and dust structure look in normal galaxies helps you interpret what you're seeing when you jump to the distant universe, where everything is compressed into faint signals. Next, Webb gets help from the universe itself, gravitational lensing. In the VV191 system, ESA Webb explains that some lensed background galaxies were so faint and so red that they went unrecognized in Hubble data, but become unmistakable in Webb's near-infrared image. Lensing magnifies and distorts distant light, and Webb sensitivity makes the magnified targets stand out. That combination does two jobs at once. It reveals distant galaxies, and it helps researchers model how mass, including dark matter, is distributed in the foreground lens. So lensing isn't just a cool visual trick. It's a measurement tool that turns extreme distance into something scientifically usable. Now for the headline that feels like it's too early to be true. The distant galaxy JADES GSZ 131. ESA Webb reports that it was discovered in deep NIRCam imaging as part of the JADES program, observed at roughly 330 million years after the Big Bang, and that researchers identified powerful hydrogen emission at an unexpectedly early time in cosmic history. The release describes how brightness across infrared filters was used to estimate redshift, and why the emission result is such a big deal. Here's the critical edge. When something is unexpectedly early, astronomers don't just celebrate, they try to break the result. They ask whether assumptions, models, or instrument limits could mimic the signal, and they look for follow-up spectra and additional targets. But if the hydrogen emission truly is that strong at that epoch, it pushes hard on our timeline for how quickly early stars and galaxies could energize their surroundings. So the meaning of the new finding isn't only we saw something far, it's that Webb's methods, structure mapping, lensing-assisted detection, and spectral fingerprints are pressing on the story of how fast the universe lit up. And that's why the next steps matter. Deeper observations, more examples, and repeat measurements that turn a thrilling clue into a stable chapter of cosmic history. If you followed the thread across the video, you've seen Webb's real superpower. It turns faint infrared light into structure you can track, chemistry you can read, and timelines you can challenge. That's why these releases aren't random highlights. They're connected clues. Now we'd love to hear from you. Are we catching rare, extreme objects that break the rules? Or are we finally seeing what the universe looked like all along, just hidden from older telescopes? Drop your take in the comments and tell me which clue felt most impossible to you. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries. Your support truly makes a difference and helps this channel grow. Thank you for watching, and see you next time.